Okay, this is going to be chapter 18, uh, refraction of light. This is section 1. Um, when light travels between two mediums, like it passes from air into water, the angle at which it's traveling changes a little bit. We call this refraction. It's also known as bending the light, but the light isn't curved when it's done. It's actually just changing the direction, the angle of the direction that it's traveling in. So we want to look at Snell's law, what we mean by this index of refraction. What does that mean? Each piece of material has a different index of refraction. And then we're going to look at total internal reflection and some various effects. One of the things would be, for instance, a rainbow that's caused by this index of refraction. So shout out goes out to Marie this time. So, hey Marie. Anyways, refraction. So change in direction of the waves at the boundary between the two mediums. So we're going to look at index of refraction, something called critical angle, total internal refraction, and so on. So when light encounters a transparent or translucent medium, some of the light is reflected, but some of it is transmitted through the medium. When it crosses into the medium, it says it bends it. Again, it just changes its direction. Here we have an example of light passing from air into water, changes its direction a little bit. Air into glass changes a little bit more. Air into a diamond a little bit more. So what can they tell us about these things? Well, each one is changing the direction a little bit more, so they're going to be a little bit different. The light bends or changes direction more when you travel from air to a diamond than the other two because of the property of these things, and we're going to investigate these properties. So when you shine a narrow beam of light at the surface of a piece of glass, again, it changes its direction as it crosses through the boundary. If it actually goes all the way through the glass, it will come out when it goes back from the glass back outside, changes the angle back, but it's offset. That's why we get this effect of the bent or the dislocated pencil. Some guys that studied this, Descartes, Snell, who got the law named after him, as well as Kepler and Galileo. So we're going to look at different angles. So we're going to refer to the angle of incidence is theta 1. That's the angle at which it strikes the surface. Remember, we measure it from the normal, not from the surface. Angle 2 is going to be the angle of reflection, or excuse me, angle of refraction. In other words, the angle it's traveling as it passes through the medium. So here we have theta 2 right there. Again, also measured from the normal. And it turns out that if we look at the ratio of the sign of these, we get a value n, which is going to be our index of refraction. I'm going to show you how the index of refraction is also calculated in a minute. So Snell found that this relationship is valid anytime we have a boundary between two materials. And we came up with Snell's law. The simple way of remembering Snell's law is the index of refraction of the first medium times the sine of theta of the angle as the light passes through the first medium is going to be equal to the index of refraction of the second medium times its theta value. As one number goes up, the other, for instance, if the index of refraction changes and goes up, then the angle has to decrease. So that's Snell's law. Again, this is just saying as n gets, if n2 is bigger than n1, then the angle is going to change, and therefore the sine of the angle is also going to change. Bent towards the normal. The direction that the ray, when it leaves the glass, is the same as it was before it struck the glass, so on the other side of the glass. So let's take a look at an example here. We have a beam of light hits a piece of glass at 30 degrees. We're going to need to know what the angle of the index of refraction is for both of the material, because we're going to use Snell's law. For air, we're always going to use 1.0. The other materials we would have to look up in some kind of chart. In this case, the angle, the n value, or the index of refraction for the glass is going to be 1.52. We now have 3 components of our 4 variable equation, and we're going to figure out the 4th. So they start with Snell's law. They like to manipulate Snell's law like this. I kind of like to just take Snell's law and substitute in. So again, I substitute in a 1 for n. I substitute in 30 for the first angle. I substitute in 1.52 for the second value of n, index of refraction, and I'm solving for x, which is the second value. So I take 1 times the sine of 30, which is 0.5, times 1.52, divide both sides by 1.52. Sine of x is equal to that, which is 0.329. If I take the so once you get that, you take the arc sine of 0.329 and you get 19.2 degrees. Make sure your calculator's set for degrees and not radians. Now they do it with just substituting in for their equation. They also get 19.2 degrees. So, looks good. Everything works. So what's the meaning of the index of refraction? Again, if we look at the relationship of the waves, if it's traveling in a vacuum, then the wavelength is equal to the speed of light divided by the frequency. Again, if we use v for the speed of light in any particular medium, c only works for the speed of light in a vacuum, so if it's in a medium we have to use v. We're going to find out what the new wavelength is. Remember, the frequency is not going to change, so something has to give, and so it would be if the frequency stays the same, the wavelength has to change. And again, a just kind of complex way of looking at it. We'll see what this says. We have the angles coming in. Again, if that's happening at a bunch of places, we could start to see where this sine wave comes from, and the fact that we have our right angle up here, and sine is opposite over hypotenuse, so we get the opposite over the hypotenuse, and we start to see where our angles come from. And again, if we start looking at some of our angles, if you're really interested, you can figure all this out. But basically, that's why we're using sine wave, is because of this again. Our right triangle and our opposite over adjacent. We start plugging in other numbers, canceling things out, and what we finally end up with is the fact that we have the ratio of the sines of each other, or the ratios of the new wavelengths. And so since the wavelength is equal to the velocity times the frequency, if the frequency stays the same, then the ratio of the sines of the angles is going to be equal to the ratio of the velocities, and therefore we can use this we could come up with these index of refractions that would also be held in ratio, which is like I said, related to the velocities. We're always going to use n in a vacuum. We're going to use n is equal to 1. We're also going to use this number for air. The velocity of the light in a vacuum is going to be the speed of light, c, 3 times 10 to the 8th. Most of the time we're going to be going from air into something else. So then we come up with an index of refraction, which is related to the comparison of the speed of light of something and the speed at which it travels in a material. This number is always going to be bigger than 1 because the fraction is going to be set up so the speed of light is the fastest something could travel, so the numerator always has to be the largest number, which means that we end up with a number that's bigger than 1 for our index of refraction. And so again, we could look at what these, solving for frequency and substituting in. Again, so now let's take a look at this idea of total internal reflection. In other words, at what angle does it have to shine so that it gets bent so far that the light doesn't come out? So here's our little movie. Okay, so the light's coming from the bottom.
The angle of refraction is larger than the angle of incidence when light passes into a medium of a lower index of refraction. As the angle of incidence increases, the angle of refraction increases. At a certain angle of incidence, known as the critical angle, theta c, the refracted light ray lies along the boundary of the two media. If you recall, when light strikes a transparent boundary, even though much of the light is transmitted, some is reflected. Total internal reflection occurs when light traveling from a region of a higher index of refraction to a region of a lower index of refraction strikes the boundary at an angle greater than the critical angle. When this happens, all light reflects back into the region of the higher index of refraction.
So to construct an equation for the critical angle at any particular boundary, we're going to use Snell's law, and we're going to substitute in the critical angle. And so the sign of the critical angle then is simply n2 over n1. The sign of the critical angle is equal to the index of refraction of the reflecting medium divided by the index of refraction of the incident medium. So again, if it's traveling into air, you'll have a 1 up there, and then you'll have a greater number down here for the material that's coming out of, like glass or diamond or whatever. And when that angle gets big enough, then all the light stays inside. So for instance, if you're looking at the surface of something underneath the water in a pool, if you're underneath the water, you might see a reflection upside down. The surface basically acts like a mirror. If you're standing and somebody is in the water at the far end, might not be visible to you like a swimmer under the water. Again, because all the light is is internally reflected. This is also the concept for fiber optics. Fiber optics, basically, we send a light signal down a piece of fiber cable, and since the material is made such that none of the light escapes, all of the light is transmitted to the other end of the optical piece of cable. You also see this in terms of mirages. Again, you're going to see when you have a cooler air and a warmer air, hotter air right next to the surface of the road, again you could see that mirage up here. As the light from a distant object travels downwards towards the road, the index of refraction of the air decreases as the air gets hotter, but that temperature change is gradual. In the case of a mirage, remember we talk about Hung's wavelets closer to the ground traveling faster than those that are higher up, causing the waves to gradually turn upwards. So sometimes we're going to end up with a superior mirage. Occurs as a reflection of a distant boat appears above the boat. Again, I've never heard of this happening before, except for this book, but I'm sure it has happened. Just like Amanda's black holes and vibrating in the key of B, I guess. So, light travels. Again, if we're looking at different temperature changes, it could actually affect the median. Now, something called dispersion. This is basically what happens when light travels through a prism. You get white light traveling through a prism. It kind of spreads it out into the rainbow. And that's because you'll notice that some of the light is going to be refracted more than others. The violet gets refracted more than the red, so the red passes through, gets changed, but not as much as the violet. We end up with our spectrum, our rainbow. It's because the speed of the violet light passing through is less than the speed of the red light passing through. Again, we see it all as white light, but actually we have all these lights coming at different speeds when they pass through the medium. The higher frequency causes it to interact differently, and the resulting is to have a slightly higher index of refraction for violet light than it does for red light. Rainbows also cause this dispersion. Again, as the white light from the sun hits into a droplet, some of it's going to pass through the light, some of it's going to be internally reflected, and since we have a bunch of it reflected, the water again is going to cause each one to be reflected a little bit differently. If you get enough of them, you'll end up with a rainbow. Again, on the way out, the light passes and is dispersed. So again, if you have enough of these droplets in the air, you could see a rainbow. Rainbow depends on the relative position of the sun, the droplet, and the observer. Again, you have to have enough droplets in the sky to cause it to have a rainbow. Sometimes you could see a faint second rainbow because the light rays are being reflected around the second time inside the droplets. Very rarely you might even see a third rainbow. And that's it.